Selamat sejahtera Dr. Azura. So this is my PSM2 project demo 1 and my title is SBMRFE for feature selection of multi-omics data for lung cancer. So in this video I will basically cover all my progress up until 24th of April 2022. This is the content of my presentation. So similar to last time, I have also divided the content into 5 parts. So the first part I will be discussing the pre-processing process. So I have updated the latest pre-processing steps. So for part 2, for feature selection, to find the best hyperparameter for SVM-RFE, I have used the grid search method to find it. So for part 3, I have the deep learning classification. So for the SDAE model, I have also updated the latest hyperparameter, but it is still an initial result. So I have collected the loss accuracy and the MSE from the result of the classification. So for part 4, I have also mentioned the problem faced during the implementation of the code. So here I have added a new problem for the Google Colab GPU constraint. So for part 5, I will show the outline for my PSM2 report. First of all, let's look at part 1 preprocessing. This is the preprocessing step in my research. So the first step is data transposition. This is because the raw data I got has inverted row and column. So in order to make the data usable, I need to invert the row and column to make sure that the column now contains the features of the omics and the row now represent the instances. So the step 2 is to remove the duplicates. So I have checked the data. There is no duplicates in the dataset. So the step 3 is to remove missing values. In this step, I have also found out that there is no missing value in the dataset. The next step is data normalization. I perform normalization basically to normalize the data into the range of 0 and 1. So part of it is because I want to also check the variance of the data. In step 5, I have used the variance threshold function to remove 0 variance feature. This time I have updated the threshold to 0 to remove only the features with no contribution. Last time I have used a threshold of 0.005 and according to doctor I have checked again. So this time I have used threshold equals to 0 so that no too many features are removed. This is how I implement the variance threshold function. So basically I initiate the variance threshold function with threshold equals to 0 and then I feed my normalized data into this function. And then after the feed function, I extract all the remaining features that it has variance not equals to 0. This is the data shape for my dataset before and after the preprocessing. So for raw dataset, we can see that the row and column are still inverted. So after transposition, the row and column are properly flipped. After that, we have the variance threshold. The gray color one is the old data shape when I was using threshold with 0.005. So this time, after the variance threshold, I have removed about 200 columns from both gene expression and mRNA expression. So compared to last time, we can see that this time in gene expression, I have removed about 4,000 less columns compared to last time and about 200 columns for mRNA. And then the last step is the integration process. I have obtained about 21,000 columns during the last time, and this time I have obtained 26,000 columns for the multi-omics data. After part 1, the pre-processing, now let's look at part 2, the feature selection. This is the method that I have used to implement SVM-RFE. So compared to last time, I have used a random hyperparameter for my SVM-RFE. So this time, I used grid search to find the best parameter for each number of feature subset. And this is done using the grid search CV function from sklearn. So for the parameter grid, I have set the C hyperparameter for SVM ranging from 0.1, 1, 10, and 100. So for the kernel of the SVM, I have used the linear kernel. And for the step for SVM RFE, I have used 1, 2, and 3. For this step hyperparameter, it is for the SVM RFE to decide how many features to remove in each iteration. So for example, if the step is 2, in every iteration, the SVM RFE will remove 2 features instead of 1. So similarly, I have decided to keep 1,000 features to 2,000 features from the multi-omics dataset. And I will record all their cross-validation score. And this time, after extracting all 1,000 to 2,000, 200,000 to 20,000 features for the multi-omics data, I will try to use all of them into my deep learning model. And to implement this SVM RFE, I have used the RFE function from the sklearn library. Next, let's discuss the steps in my feature selection process. So first of all, I have split the integrated multi-omics data into trend and test set. So for this one, I have used stratified 70% trend and 30% test split. According to many papers that I have read, most of them use 70% for trend data and 30% for test data. Their justification was because they want to allocate more data for the training process so that their model can capture, can learn the feature of the data set more efficiently, and they can use the remaining data for the test data. After splitting the multi-omics data into trend and test set, in step 2, I have performed the SVM RFE on the trend dataset to keep 1,000, 2,000 until 20,000 features. And to do this, I have used the grid search CV to find the best parameter for each feature subset. So in step 3, I have performed the cross-validation for each number of feature subset. And this is done using the repeated stratified two-fold CV with SVM as classifier. So for this classification, I have used the same hyperparameter that I have found in the previous step, which is using the grid search CV. After performing the cross-validation for each number of features, I have obtained the mean and the standard deviation score for the box plot. I have plotted this box plot just for a reference for their accuracy based on each number of feature subset. And at the end of the feature selection process, I have recorded the composition or the distribution of the feature subsets for each for different type of omics. For example, the distribution of the gene expression, DNA methylation, and the miRNA distribution. This is the result from the grid search. As you can see, this feature selection process is a very long process because for the first few iterations, it can be seen that the algorithm took 10 minutes or more just to extract, reduce 1,000 features. And in the end, the entire SVM RFE process took around 4 hours, I think. Also, according to grid search CV, the best hyperparameter for SVM RFE for all feature subset is by using the C hyperparameter of 0.1 and using SVM kernel of linear and SVM-RFE with step 1. This is the cross-validation result in box plot for each feature subset. For whatever reason, all the feature subset end up with accuracy of 1 when tested with the SVM classifier with the same hyperparameter we have found earlier. But we will see the loss function, the loss value during the deep learning classification later. Next, let's look at the omics distribution or composition after the feature selection process. On the top right corner of the screen, I have included the original composition of the multi-omics data before the feature selection process. According to the table, we can see that the composition for gene expression and mRNA expression decreases as the number of features also decreases. And on the other hand, we can see that the DNA methylation composition is increasing when the number of features decreases. The reason behind this could be that the SVM-RFE algorithm thinks that the features from the DNA methylation has more predictive power than the features from the gene expression and mRNA expression. After the feature selection process, let's look at the deep learning classification. First, let's look at the method I use for the deep learning classification. This slide is the same as the last time I have presented. So the first step is to train the autoencoder with unsupervised learning first. And then after training with unsupervised learning, I will fine-tune the autoencoder into supervised classifier. And this is done by removing the decoder part of the autoencoder and append a sigmoid layer after the latent layer. And this sigmoid layer will allow us to identify the class of the data, whether or not the patient has cancer. This is how I implement the unsupervised learning for SDAE. I have changed a little bit of things compared to last time. The things that I have changed are the number of nodes in each layer and their activation function. For the encoder, I have used 100% of input dimension for the first layer, 70% for second layer, and 40% for the third layer. And for the latent layer, I have used 10% of the input dimension. For the decoder layer, the first layer is 40% of the input dimension, the second layer is 70% of the input dimension, and the last layer is 100% of the input dimension. For example, if we use the feature subset with 10,000 features, the first layer of the encoder will have 10,000 features, the second layer of the encoder will have 7,000 features, and the third layer of the encoder will have 4,000 features, and so on and so forth. Previously, when I was implementing the unsupervised learning for SDAE, the activation function for each layer are all ReLU, which is the rectified linear unit, but this time I have changed the activation function for the last layer into a sigmoid. This is because I have referred to many sources. Most of them use the sigmoid activation function for their last layer of their autoencoder. For the SDAE fine-tuning process, as mentioned before, the decoder part of the autoencoder is removed, and instead a sigmoid layer with one output is attached to the attached after the latent layer. This allows us to predict the class of our dataset, whether it's 1 or 0, representing whether the patient has cancer or not. And the rest of the layers have no changes. For example, the encoder part and the latent layer are still using a ReLU activation function, while their input dimension are also the same. These are the hyperparameters I use for my unoptimized test run for feature subset 1000 to 10,000. For the layers, the gray color one are the old parameter, while the black color one is the latest one. So for the layers, I've used 100%, 70%, 40%, 10%, and then 40%, 70%, and 100% again. So these layers depends on the feature subset we run. So for epoch and the batch size is unchanged, which is 50 for epoch and 16 for batch size. And the optimizer is also same, which is Adam. And for the activation function, the redo activation function is used for all layers except the last layer, which is sigmoid. And for the loss function, previously I have used the MSE, which is the mean square error for the loss function. But this time, after referring to some literature, I decided to change it into binary cross entropy. At the bottom of the screen, I have also shown the parameter grid that I plan to use for the grid search. But unfortunately, I think this is not possible because it will consume many GPU RAM to perform this. But I will still try to find some workaround to see whether I can implement it or not. So this is the construction loss for the pre-training process of the SDAE algorithm based on different number of features from 1,000 to 10,000 features. To represent the construction loss for each feature subset, I have decided to plot them into graph. So for the blue line are the construction loss for the trained dataset, while the orange line is the construction loss for the validation set. From the construction loss graph, we can see that the construction loss value for both the trained and validation dataset are quite normal, except for the feature subset of 1,000 to 3,000 features, in which the construction loss for their validation dataset is higher than their training dataset. This could possibly mean that the features we have extracted for feature subset 1,000 to 3,000 are not suitable for deep learning classification according to their construction loss. This is how I do the fine-tuning for the SDAE. So for this one, I have only used the feature subset with 1,000 features. This is because the GPU RAM is already maxed, so I try to use the smallest feature subset. According to the result based on 1,000 features, the model loss is 0 for both train and test dataset. The accuracy for both train and test dataset are also 1, and the model MSE for both dataset is 0. I am not sure whether this result is valid or not, so I will need to do more research on this. Maybe I need to adjust the hyperparameter a little bit more. For the implementation of VAE, I haven't started yet, but I plan to start immediately after this presentation. Now let's look at the problem that I have faced when implementing the codes. So the very first problem faced is the severely imbalanced dataset of the multi-omics data. This problem has been mentioned last time, where it might cause problem to the deep learning classification model. The imbalanced multi-omics dataset has also caused problem during the train test split. For example, the test dataset only has one instance for class 0, while it has 103 instances for class 1. Due to the class imbalance in the train and test split, I have also faced some problem when adjusting the hyperparameter. So for cross-validation, on the train dataset I can only use twofold because the minority class only has 2 instances, while on the test set I cannot use CV at all because the minority class only has 1 instance. For SMOD, I can only use k-neighbor equals to 1 because the minority class is only 2 instances on the train dataset. And for the classification, the model can simply achieve high accuracy by predicting the majority class only, which is another problem. The next problem is insufficient GPU memory for deep learning. This is a new problem I found after implementing the SDAE algorithm. So for feature subset of 11,000 to 20,000, they cannot be used because the GPU simply have not enough memory for them. So for 20,000 features, it has nearly 1 billion nodes of parameter in the neural network. So it consumes too many GPU for the GPU to actually run. And the GPU memory also depends on the GPU availability on the Google Colab. So for example, the GPU of Tesla K80 is slower and has lower memory than Tesla K4. So the screenshot at the bottom is simply to show the number of nodes involved for the feature subset of 10,000 features, which has around 200 million nodes. The screenshot on the right shows the system usage for Google Colab when training this SDAE model. So we can see that the GPU RAM is almost full, which is why some feature subset is not able to run. The last part is my PSM2 outline. For chapter 1 to chapter 3, I think most of them are still the same. So I straightly go to chapter 4, which I will mainly focus on updating my feature selection, SDAE and VAE part of my report. Also, I have included the new variance threshold filter into my data preprocessing part. For chapter 5, I will include the performance measure that I have used to measure the performance of my algorithms. Next, I will also assess the result of the SVM RFE. And next, I will also assess the deep learning algorithms. So I will check the performance of SDAE and VAE, and then later I will compare the result obtained between SDAE and VAE. For chapter 6, I will include the achievement of my project, and then also the research constraint that I have faced during the implementation of the code. And lastly, I will also provide suggestions for improvement and the future works for future researcher. So this is the end of my presentation for PSM2 Demo 1. I am sorry if some of my explanation is not clear to Dr. So Dr. Azura, if you are curious or does not understand some part of my explanation, we can discuss it on our next online meeting. So thank you.